This screencast is an introduction to recurrence relations, and before we get started, I need to make sure that we have some common terminology notation to work with. So we'll start with defining a sequence informally as an ordered list of elements. It can be infinite or infinite, and typically by the way we order the list is by labeling them with some subset of the integers. Okay, so here's some standard examples you can keep in mind as we sort of go through this and progress in our understanding. So here's just a sequence of positive integers. Starts at 1, 2, 3, just the counting numbers. Sequence of positive even integers, 2, 4, 6, 8. Sequence of powers of 2. 2 to the 0 is 1, 2 to the 1 is 2, etc. The sequence of Fibonacci numbers. Now this is one that some of you may not be familiar with, but it has the sort of interesting way to generate each successive entry in the sequence. You start off with 0 and 1, and then you add those two previous entries together to get the next entry. So 0 plus 1 is 1, then 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, etc. And we'll see other interesting ways of generating sequences later on in the screencast. And then the final example I want you to keep in mind is reciprocals of positive integers. So we can have a sequence of things that are not integers. In this case, it's just the fractions, and these decrease down to 1 over n, and then if you keep going, of course, they'll decrease even further. So now I want to be a little bit more formal. We can define sequences. Usually we represent them by, in this way, just some arbitrary letter or word or symbol or something, and then we index it by the integers. And another way we'll write it as we can think of it as a set, and we can think of, in this case, where it starts at 1 and then just goes on indefinitely. If we want it to go on indefinitely, then we put a little infinity up there. Now, there are two ways to define sequences. Both are very important. The one that you're probably most familiar with from previous schooling is to have a formula or a rule. So in this case, let's look at the sequence an equals 2n plus 1. And if we start here at 1, n equals 1, then what do we get? We plug in 1 into the sequence and we get 3. We plug 2 into the formula for the sequence, we get 2 times 2 plus 1 is 5, etc. So it's just, in some ways, it's very similar to functions. We just plug in values and get out another value. And those values that we get out are the sequence, and so this formula gives you a way to define the sequence. There's nothing special about starting at 1. In computing, we usually start at 1 or 0 or some positive integer, but in general, you can start anywhere. You could start at minus 10, whatever. And of course, if you start at a different place, like S0 instead of S1, S being the same sequence here as AN, but starting in a different place, then the numbers are all going to be the same starting with the first entry in the sequence, but the 0th entry of the sequence gets added on. The second way, and the way that I'm really concerned with in this screencast that it's important for you to learn, is to define a sequence by a recurrence relation. Now, I'm not going to give a formal definition of that, but you can think of it as defining, if we look at this example, defining an element of the sequence in terms of earlier elements in the sequence. In this case, we just define the nth entry to be 2 times the n minus first entry, and that gives us the powers of 2. So think about this example for a minute. You might pause the slide and think about how this works. If you start at a0 equals 1, we need a starting point. Then we plug the 1 in here when n is equal to 1. Okay, so this will be, n minus 1 will be 0. We put the 1 in. 2 times 1 is 2, and so a1 will be 2, etc. So here are a couple of examples of sequences that you're familiar with that you can define using a recurrence relation. So you can think of the factorial function being defined in terms of n factorial is equal to n times n minus 1 factorial, and then you need a starting point, and that would be 0 factorial is equal to 1. So just think, I mean, if I wanted to define what 3 factorial was, that would just be equal to 3 times 2 factorial. Now that assumes I know what 2 factorial is, but that's what this general definition means. Similarly, for the powers of a, right, you can think of a to the n as equal to a times a to the n minus 1. Now if I were going to write this down in terms of the symbolism that we've been using before, I'd write it down, the recurrence relation, I write it down as a sub n is just equal to a times a sub n minus 1, okay? And the sort of starting point would be that a sub 0 is equal to 1. So think about the relationship between this formula up here, which uses the actual thing we're trying to compute, the sequence we're trying to compute, versus this uses the abstract symbolism down here that says to compute the nth element in the sequence, take a times the n minus first element in the sequence. So here are a couple examples I want you to think about, and you should pause the video here in a second. But think about this recurrence relation that looks like an equals an minus 1 plus, so the previous term in the sequence, plus 2n minus 1. And we're going to get it started with a1 equal to 1. So what I want to know is, what's the second term in the sequence, the third term, and the fourth term? So think about that, and then given, so you can go the other way, given a sequence, in this case 1, 3, 9, 27, 81, or 3 to the n, how would you define that as a recurrence relation? In other words, how would you define a sub n in terms of the terms that come before it over here, and then how would you start it up? So pause the video for a couple minutes, try to solve those problems, and then come back. So let's look at this first one now. We know that a1 is equal to 1, so to get a2, that's going to be 1 plus 2 times 2, n is equal to 2, minus 1, so that's going to be 3. So 1 plus 3, that's going to be equal to 4. To get a3, right, now that's going to be 4 plus 6 minus 1, which is 5, so that's going to be equal to 9. And then similarly to get a4, that's going to be 9 plus, if you work this out, this will be 7, and that means it'll be 16. And when you look at that, you can say, well, I know what that is. A to the n, or a sub n, I should say, is equal to n squared. So this is a formula, but this is the recurrence relation. Finally, thinking about this recurrence relation, well, again, if we're going to start at 0, we want a0 to be equal to 1. You can think of this as 3 to the 0, which is equal to 1. And then a to the n, what's a to the n going to be equal to? A to the n will be equal to 3 times a to the n minus 1. And in that way, we're going to get the powers of 3. So this slide has some important definitions related to sequences that are very helpful to know. The first one is that a sequence is called increasing if each next entry in the sequence is bigger than the preceding entry. It's called decreasing if each entry in the sequence is less than the entry that came before it. So, for example, an equals 2n plus 1 is increasing, right, because it's going to go up by 2 each time, while an equals 1 over n is going to be decreasing, right? Each fraction is going to get smaller as n gets larger. The next concept that's important is of a subsequence. Sometimes we only want to look at part of a sequence, and you obtain a subsequence by removing elements from a sequence. So, for instance, if we had the sequence of all the positive integers and we remove all the odd numbers from it, then we get a subsequence of the positive integers that looks like 2, 4, 6, and 8. we'll see lots of examples of this later in the course. Finally, I want to remind you of some notations that I'm sure you've seen before, but I want to make sure that we all are using the same notations. One is the sigma, or the sum notation, and that just uses a capital Greek sigma and has the starting point of the sum down here at the bottom and the ending point up as sort of a superscript. So this is the sum from I equals m to n of a sub I is equal to a sub m plus a sub m plus 1 up through a sub n. Very similar notation, but now we use pi, which is a capital pi in Greek, which think of p as for product. And now so this is read, the product from I goes from m to n of a sub I, and that's just going to be a sub m plus times a sub m plus 1, etc., times a sub n.